Good evening, ladies and gentlemen. How are you guys doing? So, thank you for attending this class. I know tomorrow is a public holiday again, but I will try and make this class as entertaining and informative as possible. Let's give another minute or two and see who else might join us this evening. I also want to say thank you to the students that came to see me during the consultation today. Um, a lot more students actually turned up than I anticipated. So in total, 21 students came to see me today. So it was nice to meet you. And I'm glad to see that you guys are putting effort into your moon project. So I'm proud of you guys. So you can find my office. So my office is Natural Science Building 1, the fifth floor, Physics Department, Office 68. So that's not too hard to find. So type it in the chat. So it's Natural Science Building 1. Just type it out. Fifth floor, office number 68. So the acronym they use on the maps on the campus is NW1 568. So that's where you can find me. And also, if you want a consultation session, just please send me an email. The email is usually easier because if there's a problem, I can escalate it to the HOD immediately because we need a paper trail if we need something to be escalated. And also, if you send me an email, I'm one of those persons, if I don't write it down, I forget, then I can add you into my online calendar and I can send you a meeting invite as well. So we can do virtual consultations if that is better for you. So we can do it in any platform or face-to-face consultations on campus. So in last night's class, we started talking about the Milky Way galaxy and also the family of galaxies. How do we classify galaxies? How do we distinguish one galaxy from one another? So I thought to show you guys this video that might explain it a little bit better and give you an overview of what this lecture is going to be about.
Over the past few weeks, I've talked about our sun, the planets and other objects in our solar system, stars, both big and small, brown dwarfs, exoplanets, supernovae, and clouds of gas and dust. What do all these things have in common? Well, we all live in the same town. It's a big town, and it's called the Milky Way Galaxy. Let's cut to the chase. The Milky Way Galaxy is a vast, flat, disc-shaped collection of gas, dust, and stars, a sprawling megalopolis that's a mind-crushing 100,000 light years across and several thousand light years thick. The sun is but one of hundreds of billions of stars in it, and we're located halfway out from the center in the suburbs. The disk has two major spiral arms in it and two minor ones. These come together more or less in the middle of the galaxy. Located in the center of the disk is a bar, an elongated, roughly cylindrical collection of old red stars. I know this is a lot to take in. I'll go over it piece by piece. And how we know all this, like with so many other such deep astronomical discoveries, begins simply enough: going outside and looking up. If you happen to be in a dark spot on a moonless night, you'll see a faint fuzzy glow stretching across the sky. It's brighter in some spots than others, and if the constellations of Sagittarius and Scorpius are visible, you'll notice the stream broadens there, forming a bulge apparently bigger than your outstretched hand. This glow's resemblance to a pathway or river is strong, and many ancient cultures saw it that way as well. Because it glows a dull white, the ancient Greeks called it galaxious, or milky. Over the millennia, that name stuck, and now we call it the Milky Way, or redundantly, the Milky Way galaxy. But what is that glow? It was thought to be nebulous, cloudy, until one day a guy by the name of Galileo pointed his newly crafted telescope at it. He was astonished to see that it was actually made up of stars, thousands of them. They were so close together and so faint that our naked eyes couldn't see them individually. Instead, they blended together to create that glow. Clearly, there were far more stars in the sky than the 6,000 or so visible to our unaided eyes. But how many more? And what overall shape did they form? Astronomers reasoned that counting stars in different directions might reveal the shape. If the galaxy is longer in one direction than others, you should see more stars in that direction. Over the centuries, maps were made this way, and they generally showed the galaxy to be oval-shaped, or a flattened disk, with the sun near the center. This star counting method is a good idea, but it's fatally flawed. It doesn't account for interstellar dust. As we saw in our episode about nebulae, dust absorbs visible light from stars, hiding them from our view. It's like being in a smoky room where you can't see the walls. It looks like the room is smaller than it really is, and you look like you're in the center, even if you're near one of the walls. Globular clusters were a good clue that there was more going on. These spherical balls of stars orbit the galaxy well outside the main body of the galaxy itself. There are more of them on one side of the sky than the other, which you wouldn't expect if they were evenly distributed in space. The simplest explanation was that they actually were evenly distributed in space, but it was we who were off-center. Measurements put the sun about 25,000 light years from the galactic center, which was in the direction of Sagittarius. Hey, that's where the glow of the Milky Way in the sky gets brighter and broadens out, too. Coincidence? So at this point, things were coming together. The Milky Way must be a flattened disk with a bulge in the middle. The sun is in that disk, far from the center. From inside it, we see it as a broad line in the sky. And when we look toward the center, toward Sagittarius in the sky, we see that bulge as a big blob. The disk is thinner than it is broad, so we see more stars looking into the disk than when we do looking up or down out of it. But what about the disk itself? Does it have structure in it, or is it more like a smooth, flat plate? That's hard to determine using visible light. Dust severely restricts our view. Looking into the disk, we can only see about 1,000 light years before dust blocks everything behind it. But with the advent of radio astronomy, we figured that out too. Star-forming gas clouds emit a very narrow wavelength range of radio waves, and this could be used to measure their Doppler shift, how quickly they were moving toward or away from us. Making a few other basic assumptions, their rough distance could be found as well. An amazing result was found. The locations of these nebulae indicated that the disk of the Milky Way was divided into spiral arms, huge, sweeping, curving arms that were tens of thousands of light years along their lengths. Interestingly, all the young, massive, bright stars appeared to be in these spiral arms too, with none in the apparent gaps between the arms. But that makes sense. Like all stars, these massive ones form in giant nebulae. But unlike most stars, they don't live very long before exploding as supernovae. If most nebulae are in the arms, then these massive stars will be too. They don't live long enough to get very far from their nurseries before they explode. Here's where things get a bit weird. You might want to think of the arms as structures, huge collections of stars and nebulae moving together around the galaxy's center. But that can't be right. If that were the case, they'd wind up like string on a spool, since the stars and nebulae closer to the galactic center orbit faster. But we know the spiral arms have been around a while and aren't wound up. That's because they aren't actual structures. They're traffic jams. Think about a highway with heavy traffic on it. For some reason, one car slows down a little. The car behind it slows, and the car behind that one hits the brakes too. It's like a wave that moves backwards through traffic, slowing everyone down. Where they slow down, they tend to clump up too, so you see more cars and trucks in the jam. The funny thing about traffic jams is they tend to persist for a long time, even as cars move out of them. The car at the front might slow for a moment, then accelerate away. But the cars behind it are still moving slowly, and more cars are piling up in the rear. For every car that leaves the jam at the front, another enters from the back. Even though the actual individual cars come and go, the jam persists. Spiral arms are the same sort of phenomenon. The initial wave, the jam, may be started by some sort of disturbance in the disk, perhaps an overdense region created when a couple of giant molecular clouds smash together. Once created, this effect propagates outward like a ripple in a pond and gets sheared into a spiral wave pattern by the rotation of objects in the disk. Stars and nebulae enter the wave, pile up a bit, move through it, and then resume their merry way once they leave it. Our sun takes about 250 million years to orbit the galaxy, which means it's made about 20 orbits since it was born. It's moved in and out of spiral arms many times over its long life. That's why spiral arms don't wind up. The arms are waves made of objects in them, but the objects themselves are transient. However, there's more to it. A nebula entering a spiral arm might hit another one already in there, a cosmic fender bender. But when that happens, the nebulae can collapse, forming stars. Some of them are massive, luminous, blue, and hot. These stars are very easy to spot at great distances, making the galaxy's spiral arms blue. They also light up the gas around them, accentuating the spiral arms. Spiral arms are where the majority of starbirth occurs in the galaxy, which helps maintain the spiral pattern. They're the ultimate crowdsourced projects. After all that, it's actually hard to say how many spiral arms the Milky Way has. It's been thought to have 2 for a long time, but a recent study of the locations of star clusters seems to indicate there are actually 4. Milky Wayologists are still arguing about it, but either way, there are also short spurs that stream off of the major arms as well. Our sun is located just outside one of these smaller arms called the Orion Arm. Mapping the galaxy's spiral arms is ongoing work, and it's kind of a mess. It's like being inside a hurricane and trying to figure out its structure. But we're doing pretty well so far. In the center of the galaxy is the bulge. Recent observations indicate this is actually a cylindrical bar of redder stars that's pointed nearly directly at us, so it looks more circular to us. This region is very old. All the starbirth in there happened long ago and ceased when the gas ran out. Unlike the spiral arms, where stars are still actively being born, all the blue stars in the bar are long dead, exploded, leaving behind billions of lower mass, redder stars. The bar is probably about 20,000 light years long. This odd structure is due to the weird gravity of the galactic disk. Unlike our solar system, where the central sun dominates the gravity of the galaxy is spread out over a huge area. This distribution of stars and gravity means weird structures can pop up and self-maintain, like spiral arms and central bars. Unlike the arms, though, the bar rotates as a single unit. Stars near the edge make one orbit in the same time as the stars closer in. In the very center of the galaxy sits a very massive black hole, one with 4 million times the mass of the sun. This might seem huge, but remember, the galaxy has hundreds of billions of stars in it. The central black hole is actually just a teeny tiny part of the galaxy by mass, but we'll learn more about it in a future episode and see may have played a very big role in our galaxy's formation and evolution. The last component of the Milky Way is its halo, a vast spherical cloud of stars surrounding it out to great distance, more than 100,000 light years. We don't know much about the halo, but we know the stars in it are old. No star formation occurs there, so any stars we do see would be old. It's possible some stars in the halo formed there, while others were flung out into the halo after collisions with other stars and clusters. Speaking of which, most of the globular clusters orbiting the Milky Way are in the halo. There are more than 150 in total. So there you have it, our local galactic town. But like any denizen of a small town, it's natural to wonder if this is all there is. What else is out there? And at the beginning of the 20th century, astronomers started to ask the same thing. Is the Milky Way the galaxy? Or a galaxy? Oh, we're about to take a big step here with Crash Course Astronomy. A really big step. Better strap in. Starting with the next episode, the universe We live in a pretty cool neighborhood, the Milky Way galaxy. We're out in the suburbs, sure, but it's still an interesting place, buzzing with activity. Stars, nebulae, stellar clusters of various sorts, the occasional supernova. It's a happening place. In the earliest part of the 20th century, astronomers were just starting to figure this all out. But there were a handful of objects that were puzzling. Dotting the sky here and there were faint fuzzies displaying a variety of shapes. Some were round, some elongated, and some even seemed to have spiral arms. Even with big telescopes, they looked smoky, so they were simply called nebulae. Their existence was puzzling, though. What were they? How did they form? Were they big, small, near, far? Eventually, astronomers had uncovered the key to these objects, and in one fell swoop, our universe got a lot bigger. A lot. In 1920, there were two competing ideas about the universe. One was that our Milky Way was it, and that everything we saw was in it. The other was that these spiral nebulae seen in the sky were also like our Milky Way, island universes in their own right. Two astronomers debated this controversy in that year. Harlow Shapley argued that the Milky Way was all there is, while Heber Curtis was of the opinion that we were one of many galaxies. It wasn't a debate as such, more of a presentation of ideas, and there was no clear winner. Both sides had fragmentary data, and we now know some shaky observational evidence that turned out not to be correct. For example, Shapley noted that one of the spiral nebulae had been seen to rotate, so it must be small. It turns out that was just wrong, dead wrong. On the other hand, Curtis noted that if galaxies were as big as Shapley claimed, hundreds of thousands of light years across, then other galaxies must be impossibly far away. But hello, galaxies really are that big, and they truly are mind-numbingly distant. The observation that finally unlocked this mystery was made just a few years later when Edwin Hubble and Milton Humason observed the great spiral nebula M31 in Andromeda, using what was at the time the largest telescope in the world. They found dozens of pulsating stars in it, literally stars that change their brightness in a regular periodic fashion. These are called Cepheid variables, and they were critically important because it was known that the time it took them to pulse was directly related to their luminosity, how much energy they emitted. That means if you can measure their period, you can determine how far away they are simply by measuring their apparent brightness. The distance they found to M31 was 900,000 light years, clearly outside even the largest estimates of the size of the Milky Way. They also resolved swarms of faint stars, cinching the fact that the Great Andromeda Nebula was actually the Andromeda Galaxy. At that moment, our understanding of the universe swelled in size, and we've never looked back. We've learned a lot about galaxies in the ensuing century or so. Each is a collection of at least hundreds of millions or even trillions of stars, and most contain some amount of gas and dust. They range in size from tens of thousands to hundreds of thousands of light years across, and they come in a variety of shapes. We use these overall shapes to classify them. Broadly speaking, there are four major types of galaxies: elliptical, spiral, peculiar, and irregular. Spiral galaxies we've seen. We live in one. These are characterized by broad, flat, rotating disks of stars, gas, and dust, a central bulge of older, redder stars, sometimes with a long cylindrical or rectangular bar of stars as well, and a huge extended halo of older stars. Some spirals have large central bulges and some have much smaller ones. Most have bars of stars extending across the central part of the galaxy. Our Milky Way does. The spirals come in a variety of flavors as well. Grand design spirals have magnificent, well-organized spiral arms that extend from the very center out to the visible edge of the galaxy. Others have choppy or patchy arms. These are called flocculent spirals, resembling tufts of cotton. Some spirals have wide-flung arms, while others are tightly wound. Spirals take on wildly different appearances depending on their angle to us. Some we see face-on, and these may be the most magnificent objects in the entire sky. Huge and sprawling, their structure is obvious and easy to see. Star-forming nebulae are laid out like beads on a string, colored pink by the characteristic glow of warm hydrogen. Young, massive, luminous stars blaze blue, tracing the spiral's form. Filigrees of dust clouds align with the arms as well, and the central bulge or bar glows an eerie reddish yellow. The star formation there long since ceased. The bluer stars all exploded, leaving only the redder stars behind. When spirals are more tilted to our line of sight, some of this structure is hidden, And when they're edge on, we see them as the flat disks they truly are. Dust clouds are tightly restricted to the midplanes of spiral galaxies, and we sometimes see them bisecting the galaxy like a racing stripe right down the middle. The reason for this is the same reason our solar system is flat. Galaxies probably formed from huge clouds of gas billions of years ago. As a cloud collapses, small eddies in the gas would get amplified and would create an overall spin. This naturally leads to a flattening of the cloud, and by the time the stars in the galaxy were starting to turn on, the overall structure of a flat disk was in place. Elliptical galaxies are, well, elliptical. Kinda. Some are nearly spherical, gigantic cotton balls of billions of stars. Others are more elongated, shaped like cigars or American footballs. They tend to have no overall structure as spirals do. Ellipticals are puffy, and they range in size dramatically. Some are what are called dwarf ellipticals, just a few thousand light years across, to monsters that hugely outmuscle our own Milky Way. Besides their shape, ellipticals are characterized by a lack of gas and dust in them, and also are populated with older stars. Apparently, star formation in ellipticals came and went eons ago, and all the young massive stars have long since exploded, leaving less massive redder stars. This makes them similar to the stars in the central bulges of spiral galaxies. It's not exactly clear how ellipticals form. Current thinking is that they are the products of, and this is mind-blowing, galactic collisions. Yes, you heard me, entire galaxies collide. When galaxies collide, it's a train wreck on a cosmic scale. Galaxies are huge structures, and with hundreds of billions of stars in them, their gravity is pretty strong. If two galaxies get close enough together, they can draw each other in and collide. A galactic collision is a weird event. Even though the collision speeds can be hundreds of kilometers per second, the event plays out over hundreds of millions of years. Remember, we're talking about distances of tens of thousands of light years here. In the early stages of the collision, tidal effects can be strong. Stars on the side of the galaxy near the other one get pulled toward it more strongly than the stars farther away, so the galaxies can get stretched and long tendrils of stars and gas get drawn out. Generally, collisions aren't head-on, but more of a side swipe, so there's some sideways motion. When that happens, the tidal streamer can become curved, a long, graceful arc. Colliding galaxies in this stage form all sorts of bizarre and spectacular shapes. Sometimes the galaxies separate and then fall back together again. When that happens, the main bodies collide. But this isn't like two cars crashing together. Stars are very, very small compared to the space between them. So even though hundreds of billions of stars can be involved, the odds are good that no two stars will ever physically hit each other. Space is weird. Gas clouds, though, are huge, and they do collide. They slam into each other, collapse, and form stars at a furious rate. Colliding galaxies can glow pink and blue as stars are born and light up the hydrogen clouds around them. Sometimes the two galaxies will collide at high enough velocity that they pass right through each other. But even then, in most cases, they'll slow, stop, and then recollide. Eventually, they merge, their huge energies of motion absorbed by the orbiting stars, puffing them up into vast, sweeping orbits. The results, so we think, are elliptical galaxies. Not all collisions result in galaxies becoming ellipticals. If a big spiral collides with a much smaller galaxy, it can tear apart the interloper and literally absorb it into itself. So galaxies are cannibals. We think most large galaxies grew to their current bulk by consuming smaller galaxies, including our own Milky Way. In fact, we have proof. We're currently in the process of eating several smaller galaxies right now. Terzan 5 is a small knot of stars that may be the leftover core of a galaxy cannibalized by our own. And two huge looping streams of stars circling our galaxy are parts of the Sagittarius and Canis Majoris dwarf galaxies being torn apart by the Milky Way. This brings us to the third type of galaxies, peculiars. These are not shapeless really, but have a shape that's weird. Peculiar galaxies are essentially all due to collisions. Colliding galaxies clearly have structure, but can be all sorts of odd, distorted shapes. Sometimes a small galaxy will plunge right through the heart of a much larger galaxy. The gravity of the smaller galaxy draws in stars and then flings them away in the bigger one, like ripples in a pond. The result is a ring galaxy, sometimes with the culprit intruder seen nearby. The famous Cartwheel galaxy is a fine example of this. Another is Hoag's object, though to be honest, it's not completely clear if this bizarre galaxy is a product of a collision or some other process. It's peculiar either way. Finally, we come to galaxies that truly are shapeless, called irregular galaxies. These tend to be small and chaotically shaped. Bigger ones may be victims of collisions, their shapes distorted so much that the structure was lost. Smaller ones may simply be too tiny to collect themselves together into a recognizable shape. Many galaxies have companion satellite galaxies. The Milky Way has a couple of dozen such satellites. The two biggest are the Large and Small Magellanic Clouds, visible from the southern hemisphere. Both are irregular in shape, though the Large Magellanic Cloud is barely coherent enough to qualify as a disrupted, though small, barred spiral. Both are riddled with gas and dust. The Large Cloud sports the biggest and most active star-forming gas cloud in any nearby galaxy, the Tarantula Nebula. It's producing so many stars that astronomers think it may be in the process of forming a globular cluster. There are other types of galaxies as well. Some, called active galaxies, pour out far more energy than normal ones. And galaxies aren't just scattered evenly across space. They tend to be found in clusters. Some contain thousands of galaxies. We'll get to all that in the next episode. We now know that the universe is far, far larger than just our Milky Way galaxy. It's a recurring theme, isn't it? We thought the Earth was the center of creation, and then the sun, and then the galaxy. But every time we investigate these situations earnestly and engage in honest debate, we find that we're smaller and farther removed from the action than we thought, or than we thought we deserved. Hey astronomers, Phil Plait here. In our last episode, I talked about galaxies, vast collections of gas, dust, and upwards of hundreds of billions of stars. We live in one, the Milky Way, a gigantic disk galaxy with sprawling spiral arms. Other galaxies are elliptical or irregular or peculiar, but those are classifications based on shape. We also classify galaxies on their behavior, and sometimes even on their location and mass. To understand why, we have to take a step back and look at the environments in which galaxies sometimes find themselves. And if you thought galaxies were big and powerful, well, I'm about to crush your brain again. In the 1960s, a peculiar object was found called 3C273. Through optical telescopes, it looked like an unassuming blue star, but through a radio telescope, it was seen to be ablaze with light, a luminous powerhouse. Stars didn't blast out that much radio radiation, so this was baffling. The mystery deepened when spectra of 3C273 were taken. It wasn't a star, it was an entire galaxy. And not just any galaxy, but one very, very far away, well over 2 billion light years. Far from being some dim thing, 3C273 revealed itself to be the most luminous object in the universe ever seen at that time. It blasts out over 4 trillion times the energy the sun does. And yet it appears star-like, a mere dot in the sky. Because of this, it was dubbed a quasi-stellar radio source, which is pretty underwhelming for the most powerful energy source in the entire cosmos. Happily, the name was shortened to quasar, which, you'll admit, is way cooler. Once 3C273 became known, lots more such objects were found. With the advent of X-ray observatories launched into space, even more energetic point sources were found, which is amazing. X-rays are a very high energy flavor of light, and it takes a lot of power to make them. Eventually, galaxies like these were even found to be blasting out gamma rays, the very highest energy kind of light. Clearly, these were no regular galaxies. Astronomers gave them the generic name active galaxies and classified them into various subcategories depending on how they emitted their light and what kind of spectra they had. But what could power these immensely energetic galaxies? It turns out to create that kind of energy, you need to have an object with a lot of gravity. And what kind of object has a lot of gravity? In the 1980s, astronomers were getting suspicious that all large galaxies had very massive black holes in their cores. In fact, one of the reasons the Hubble Space Telescope was built and launched was to explore this idea and characterize, that is, find out as much as it could about, these black holes. Over time, we've found this idea is absolutely correct. Every big galaxy we see appears to have a huge black hole in its heart. Even the smallest is a monster with millions of times the sun's mass, and some tip the cosmic scale at billions of solar masses. We now think that these supermassive black holes form at the same time galaxies do. As the material coalesces to create a galaxy, some falls to the center and feeds the black hole there. It grows as its host galaxy does. But I can hear you thinking, hey, Phil, don't black holes suck down everything, even light itself? How could they power active galaxies, the brightest objects in the universe? You can't escape from a black hole once you fall all the way in. Just outside the black hole's event horizon, things can still get out. If a black hole is sitting all by its lonesome out in space, it's, well, black. But if matter, like gas, dust, or even whole stars, falls into the black hole, it can be shredded by the fierce gravity. This material forms a flat disk called an accretion disk, the matter swirling madly at ferocious speeds before falling in like water down a bathtub drain. Stuff closer to the black hole orbits faster than stuff farther out. This means material in the disk rubs together and heats up, just like rubbing your hands on a cold day warms them up via friction. But around a black hole, the orbital speeds are near the speed of light. Try rubbing your hands together at a couple of 100,000 kilometers per second and see how much heat you make. So friction and other forces heat the material falling in to millions of degrees, so hot that it blasts out light across the electromagnetic spectrum. And that's what powers active galaxies. The black hole is the energy source, but the matter falling into it is the actual light bulb. Active galaxies are so bright they can be seen clear across the universe. Not only that, but some active galaxies have jets. Magnetic fields coupled with the incredible rotation of the accretion disks can launch twin beams of matter and energy directly away from the black hole along the poles of the disk. These beams pack a huge wallop, traveling for hundreds of thousands of light years. Eventually, they slow down as they ram through the thin material between galaxies. But when they do, they puff up. They look like huge cotton swabs which glow in radio waves. Active galaxies can look pretty different from each other, and we now think that's due to our viewing angle on their accretion disk. When we see it edge on, the thick dust in the disk blocks the intense highest energy light, but we do see lots of infrared as the radiation from the disk heats up clouds of dust around it. If the accretion disk is tipped a bit to our line of sight, we see more optical and high energy light from it. And if the poles are aimed right at us, all that ridiculously energetic X and gamma ray light can be seen. The Milky Way has a supermassive black hole in its heart too, with a mass of over 4 million times the sun's. That might sound huge, but remember, the galaxy has hundreds of billions of stars in it. The black hole is only a teeny tiny fraction of the total mass of the Milky Way. Our black hole is quiescent, that is, not actively feeding, so we're not an active galaxy. Every now and again, we'll see a flare from it as it swallows down a gas cloud or something like that, but nowhere near what's needed to switch it fully on. Happily, we appear to be safe from any tantrums it might throw, but that may not always be the case. One way to flip such a black hole from milquetoast to monster is through galactic collisions. When two galaxies collide, a lot of gas can be dumped into their centers where it can be gobbled down and heated up. We do see a lot of evidence that active galaxies are disturbed, as if they recently collided. So, could that happen to us? Yes. Yes, it can. In fact, it will. But not for a few billion more years. To understand that, we have to take a small step back. Well, actually a huge step back, a few million light years, and take a look at where galaxies live. Our Milky Way isn't alone. It's part of a small knot of galaxies we call, in long, boring astronomical nomenclature tradition, the local group. It consists of a few dozen galaxies, most of which are small and dim, so faint that we're still discovering them. Two galaxies completely overpower the group: the Milky Way and the Andromeda Galaxy. The local group is elongated, almost dumbbell-shaped, with the Milky Way on one side and Andromeda on the other. In the past, the local group probably had lots more galaxies, but over the eons, the two big galaxies ate them all, growing huge. Andromeda is bigger than we are and has more stars, but honestly, we're both pretty big as galaxies go, and someday we'll be bigger. The Andromeda Galaxy is about 2.5 million light years away, close enough that it can be seen by the naked eye on dark nights, the most distant object easily seen without aid. Spectra taken of Andromeda reveal an interesting fact. It's headed right for us! Its spectrum is blue shifted, meaning it's approaching us, and it's doing so at quite a clip, about 100 kilometers per second. That's fast, but 2.5 million light years is a long way. The collision is inevitable, but it won't happen for several billion years. When it does, both galaxies will stretch out galactic tides, forming long curved streamers of stars. They may pass by each other during the first pass, but over the next few 100 million years, they'll slow, fall back toward each other, and merge. They'll then form one much larger galaxy, probably an elliptical, which astronomers have called Milkomeda. I know that's awful, but if you can come up with a better name, let us know. Anyway, although this won't happen for billions of years, that's still long before the sun dies. The Earth may still be around when the galaxies collide. It's not clear what will happen to us. The sun may continue to lazily orbit the core of the new galaxy, or it may move farther in toward the center or farther out in the galactic suburbs. And here's another fun fact. Andromeda has a gigantic black hole in its core too, which has 40 million solar masses, 10 times the mass of ours. When the galaxies merge, the two monsters will probably go into orbit around one another. Not only that, but any gas and dust left over from star formation during the collision may fall toward the center of Milkomeda, where the two black holes will gobble them down and may turn the galaxy into an active one. Hopefully, any death rays launched from that will miss Earth, but that won't happen for like 4 billion years anyway. I'm not too concerned over the fate of the Earth at that point. I feel that right now is a good time to give you a heads up. We're about to take a very, very big step. Up to this point in the series, we've talked about some pretty big distances. Millions or billions of kilometers to the planets, trillions of kilometers to the stars, and then jumping to thousands of light years, quadrillions or quintillions of kilometers when talking about the galaxy itself. But those distances are as nothing when you start talking about intergalactic trips. We're about to venture out into the greater universe, and things are about to get very large. When we step outside our Milky Way, we find that a few galaxies have clumped together to form the local group. But as we look farther out into the universe, we see that galaxies tend to clump together on larger scales as well. Many are in small groups like ours, but sometimes they aggregate into much larger galaxy clusters. A typical galaxy cluster is a few tens of millions of light years across and can contain thousands of galaxies. The nearest one to us is the Virgo cluster, located about 50 million light years away in the direction of the constellation Virgo. It has well over 1,000 galaxies in it, maybe twice that much. It may have as many as a quadrillion stars in it. Like star clusters, galaxies and galaxy clusters are bound to the cluster by their own mutual gravity and move through the cluster on long orbits that can take billions of years to complete. Thousands of clusters are known, and they contain every kind of galaxy imaginable. Spirals, ellipticals, irregulars, peculiars, active galaxies. In many clusters, a huge elliptical galaxy sits right at the very center. This is probably the result of collisions between smaller galaxies. When they smack into each other, their velocities through the cluster tend to cancel out, like two cars hitting head-on and stopping, so they fall to the center. As more mass falls to the center, the galaxy there grows huge. As mind-boggling as this all is, we're not done. Surveys of the sky have revealed that not only do galaxies clump together in clusters, but clusters themselves fall into even bigger groups called superclusters. A supercluster usually has several dozen clusters making it up, and are hundreds of millions of light years across. Our local group is near the Virgo cluster, and both are part of the Virgo supercluster. Recent observations indicate the Virgo supercluster is actually only an appendage of the even larger Laniakea supercluster, which may have 100,000 galaxies in it, stretching across 500 million light years. This new result is a bit controversial. I mean, it's hard to know exactly how big such a structure is, especially when we're inside it. But it gives you an idea of the vast sizes and distances we're talking about here. Superclusters themselves aren't just randomly distributed through the universe either. They appear to fall along tremendously long, interconnected, and intersecting filaments, making the universe appear almost foamy on the biggest scales, like a sponge. In between the filaments are vast regions relatively empty of galaxies called voids. This cosmic large-scale structure, its size, shape, distribution of matter, and more, holds clues to some of the biggest questions we can ask. What is the universe made of? How did it start? What is its eventual fate? These are questions we'll get to in future episodes very soon, and I promise you they'll stretch your mind like nothing you've ever encountered before. But before we wrap up, there's one more thing I want you to see. When you look at all these pictures of galaxies, of clusters, of superclusters, a question pops up. How many galaxies are there? Can we count them all? To help answer that question, back in the 1990s, astronomers used the Hubble Space Telescope. They pointed it toward the emptiest part of the sky they could, a spot with little or no stars, nebulae, or galaxies in it. They then let it stare, simply collecting light from whatever it could see, letting light accumulate until incredibly faint objects could be detected. And what did it find? Wonder. Pure, simple wonder. Oh, yeah, and thousands of galaxies. This is the Hubble Deep Field. Mind you, the area of sky you see here is roughly the same as the apparent size of a grain of sand held in your palm with your arm outstretched. And yet, in that tiny section of sky, there are thousands of galaxies. Essentially, everything you see in that image is a galaxy, a huge collection of gas, dust, and billions of stars. The deep field was repeated in different parts of the sky, and the result was always the same. Crowds of galaxies jostling for position, crammed together even in a tiny slice of the heavens. You can count all the galaxies in these deep fields and then use them to extrapolate to the entire sky, giving you the total number of galaxies in the universe. And what do you get? Well, give or take, 100 billion galaxies. 100 billion. And each with billions of stars. The universe is mind-crushingly huge. And yet here we are, a part of it, learning more about it all the time. It's easy to think the universe is too big to comprehend and makes us seem tiny and insignificant in comparison. To me, the opposite is true. It's our curiosity about this enormous cosmos that makes us significant. We yearn to learn more, to seek out knowledge. That doesn't make us small. It makes us vast. Today you learned that active galaxies
So that is very cool, right? So that is a brief overview of what we will be discussing in this lecture and also a few of the upcoming lectures. You have a question? Yes, go ahead. So while you are typing your questions, just a few things that I saw in comments. So a question is not an afterlife or other life, but like other universes or something beyond the known universe. So yes, of course, we don't know what's happening beyond the known universe, and there's theory for multi-dimensions and multi-dimensional universes, I mean there's more than one universe. So yes, there are other other possibilities out there as well. And let's go. Astronomy has made numbers seem silly to me. Yes, that is also very true. So Ms. Naledi, I'm just waiting for your question. And while you're typing your question, or you can even unmute your mic and ask a question, whatever you prefer. We ended last night. Okay, so what certainty is there that Andromeda Milky Way will merge? Seeing that Andromeda is much larger, won't it just absorb the Milky Way? So we can do the math and calculations. And from that math, we can create mathematical models and simulations. So we are 100% certain that the two galaxies will merge. So last night, this slide. So what are the properties of galaxies? What are the diameters, luminosities, and masses? Just as in a study of stellar characteristics, the first step in a study of galaxies is to find out how far away they are. Once you know the galaxy's distance, its size, and luminosity are relatively easy to find. Later in this section, you will see that just as for stars, finding the masses of galaxies is more difficult. So now we're going to look at distances. So the distances to galaxies are so large that it's not convenient to measure them in light years, parsecs, or even kiloparsecs. Instead, astronomers use the unit megaparsecs to speak about these distances. So when 1 megaparsecs equals 3.3 million light years, or approximately 3 to the power 10 to the power 3 times 10 to the power 19 kilometers. So here we can see a distribution of galaxies in this image. So here we can see in the X direction, we have megaparsecs, and in the Y direction, megaparsecs. So to find the distance to a galaxy, astronomers must search amongst its stars, nebulae, and star clusters for familiar objects whose luminosity they know. Such objects are called distance indicators because they can use to find the distance to a galaxy. Astronomers often refer to them as standard candles. If you can find a standard candle in a galaxy, you can judge a distance. Shaped variable stars are reliable distance indicators because their period is related to their luminosity. The period luminosity relation has been calibrated so you can use the period of the star's variation to find its absolute magnitude. Then, by comparing its absolute and apparent magnitudes, you find its distance. So in this image, we can see the vast majority of spiral galaxies are too distant for Earth-based telescopes to detect Shaped variable stars. The Hubble Space Telescope, however, can locate Shapeds in some of these galaxies. For example, in a bright spiral galaxy M100. From a series of images taken on different dates, astronomers can locate Shapeds, determine a period of pulsation, and measure the average apparent brightness. They can then deduce the distance to the galaxy. So in distance for this galaxy, so M100, it is 16 megaparsecs. So just before I forget, another comment I saw in the chat is, can we see Sagittarius A star with the naked eye? Unfortunately not. Sagittarius A, or the supermassive black hole, is number one. It's blocked by interstellar dust, so we can't see it with naked eye, but we can see it with a radio telescope. And then secondly, when the Event Horizon telescope shows a galaxy, a supermassive black hole to take a picture of and observe, I think it was M86, that galaxy was chosen because we are staring directly down the barrel. We are looking directly into the black hole. But in a Milky Way galaxy, we are seeing the black hole from the side, and that makes it a little bit more difficult, but not impossible to see. So sorry, but this relates to the Moon project. Here we're struggling to get pics of the Moon in 10 days in a row. Can we use an online virtual telescope to get pictures of the Moon at the same time in the same direction? To still see the pattern, but still link that to a real world position and picture to have the markers in real life in order to draw the Moon orbit path related to your world position and get it shape? Yes, you are allowed to do that. So if you can extrapolate from that image where everything is and you still make a drawing, then yes, you are more than welcome to do that as well. So even with the Hubble Space Telescope, Shapeds are not visible in galaxies much beyond 30 megaparsecs. So astronomers must search for less common but brighter distance indicators and calibrate them using nearby galaxies that contain both indicators. For example, by studying nearby galaxies with distances known for Shapeds, astronomers found the brightest globular clusters have absolute visual magnitudes of -10. If you found globular clusters in a more distant galaxy, you can assume that the brightest of the globular clusters have absolute magnitudes of -10 and use that information to calculate the distance. So astronomers can calibrate type 1a supernovae, those produced by collapse of a white dwarf, because the white dwarf always collapses at the same mass limit. So the explosions reach approximately the same maximum luminosity. When a type 1a supernova occur in galaxies with distances that are known from Shaped variables and other distance indicators, astronomers can find the absolute magnitude of the supernovae at peak brightness. An example is shown in figure 13.4. When astronomers see a type 1 supernovae in a more distant galaxy, they observe the apparent magnitude of the supernovae at maximum and compare that with known absolute magnitude, these supernovae reach a maximum to find the distance to the galaxy. So here we can see in this image, so while dinosaurs roamed Earth, a white dwarf in a galaxy NGC 1309 collapsed and exploded as a type 1 supernovae. And the light from the explosion reached Earth in 2002. Astronomers found Shaped variable stars in the galaxy, so you can determine that it is 120 million light years away. And that allowed him to find the absolute magnitude of the supernovae at its brightness. The supernovae had faded from view 3 years later, but though the second image was made using the Hubble Space Telescope, by combining observations of many supernovae, astronomers have been able to calibrate type 1 supernovae as distance indicators. Is everyone still following? Awesome. So notice how astronomers use calibration to build a distance scale, reaching from the nearest galaxies to the most distant visible galaxies. Often astronomers refer to this as the distance pyramid or the distance ladder, because each step depends on the steps below it. The most dependable step is the Shaped variable star. But notice that Shaped distance indicators depend on astronomers' understanding of stellar luminosities and of the stars in the HR diagram. And that rests on an even lower step in a ladder, measurements of the parallax of stars. Stellar parallax in turn depend on measuring the size of Earth's orbit around the Sun, which finally rests on the bottom step, measuring the size of Earth itself. The distance ladder ultimately connects the size of Earth to the most distant galaxies in the universe. So why is it called a type 1 supernovae? So if you go back a couple of lectures, we talked about novae. We learned there are different classifications for a novae. So if a galaxy has above a certain mass and it collapses into a white dwarf, then it is a type 1 supernovae. So putting us all together, so going back a couple of lectures, we started, I don't know if you remember, in one of the first slides, I showed you a picture of a woman laying on a grass and started zooming out meters and a couple of meters and a couple of kilometers. And so we can see the galaxy and then clusters of galaxy. And I did the same thing with Google Earth and screenshots I took on campus and where we are. Now we can see how everything is actually fitting in together. So the most distant visible galaxies are over 3,000 megaparsecs, so that meaning 10 billion light years away. And at such distances, you see an effect akin to time travel. When you look at a galaxy that is millions of light years away, you do not see it as it is now, but as it was millions of years ago when its light began the journey towards Earth. So when you look at a distant galaxy, you look back into the past by a amount called the look-back time. A time in years equal to the distance in light years, the light from a galaxy traveled to Earth. So looking back in time, the further we look away, the further back in time we see. So for example, it takes roughly about 8 minutes for sunlight from the sun to reach us at Earth. So that means when we look at the sun, we have a look back time of 8 minutes. Everyone still following? Awesome. So the look-back time to nearby objects is usually not significant. For example, the look-back time across a football field is a tiny fraction of a second. The look-back time to the moon is 1.3 seconds. The sun, only 8 minutes. And to the nearest star, a bit over 4 years, so Alpha Centauri. So the Andromeda Galaxy has a look-back time of over 2 million years. But that is a mere eye blink in a lifetime of a galaxy. If you look at more distant galaxies, the look-back time becomes an appreciable part of the age of the universe. So now we are going to look at the Hubble law. So although astronomers must work carefully to measure the distance to a galaxy, they often estimate such distances using a simple relationship that was first noticed about the same time astronomers were beginning to understand the nature of galaxies. Early in the 20th century, astronomers were able to record a spectra of brighter galaxies, most as redshifts, as if they were receding. The faintest galaxies had larger redshifts. In the 1920s, astronomers Edwin Hubble and Milton Emerson were able to measure the distances to a number of galaxies using Shepard variable stars. And in 1929, they published a graph that plotted the apparent velocity of recession versus distance for the galaxies. So here we can see Edwin Hubble and Milton Emerson first diagram of the apparent velocities of recession and distances of galaxies did not probe very deeply into space, and the horizontal axis was later recalibrated. The data did show, however, that the galaxies are receding from one another. The simple relationship between apparent velocity and recession and distance is known as the Hubble law, and the slope of this line is called the Hubble constant. So here we have the velocity in kilometers per second of the galaxies. Here we have the distance between them. So that means the gradient or slope of this line is the Hubble constant. So the Hubble law has an important implication. It is commonly interpreted to show that the universe is expanding. The distance to a galaxy can be found by dividing its apparent velocity of recession by the Hubble constant. This makes it relatively easy to estimate the distances to galaxies because a large telescope can record a spectrum of a galaxy and determine its apparent velocity of recession, even when it is too distant to have visible distance indicators. Edwin Hubble's original measurements of h, so the Hubble constant, was too large because of calibration errors in his distance measurements. The most precise modern measurements of the Hubble constant yielded the value of 70 kilometers per second per megaparsec, with uncertainty of just a few %. Yes, I agree, but it's just for explanation. So this year I'm not teaching I think module is PHY214, I think. But that is basically Introduction to Astrophysics. I taught that back in 2020 as well, but I'm not teaching it this year. This year, Dr. Forat is teaching it. But for that model, for one of your practicals, I set up a question where you guys need to use the Hubble constant and Hubble's law to determine the age of the galaxy. That's actually a very nice prac to do, but hopefully Dr. Forat will use that in this year's lectures and next year's lectures. So now we're going to look at the diameter and luminosity of galaxies. So once you find the distance to galaxy from distance indicators or Hubble law, you can calculate its diameter and its luminosity. With a good telescope and the right equipment, you could easily photograph a galaxy and measure its angular diameter in arc seconds. If you know the distance, you could use the small angle formula, so reasoning with numbers 3.1, to find its linear diameter. If you also measure the apparent magnitude of the galaxy, you could use the distance to find its absolute magnitude, and from that, its luminosity. The results of such observations show that galaxies differ dramatically in size and luminosity. Irregular galaxies tend to be small, 5 to 25% the size of our galaxy, and of low luminosity. Although they are common, they are easy to overlook. Our Milky Way galaxy is large and luminous compared with most spiral galaxies. Though astronomers know of a few spiral galaxies, that are even larger and more luminous. So teach it next year, please. I wish I can teach it. It all depends on the HOD and what the teaching plan is for next year. But there's a 50-50% chance that you guys might get me next year in that second year module. So the largest is nearly 5 times bigger in diameter and about 10 times more luminous than Milky Way. Elliptical galaxies cover a wide range of diameters and luminosities. The largest, called giant ellipticals, are 10 times the diameter of our Milky Way. But many elliptic galaxies are very small dwarf ellipticals, only 1% diameter of our galaxy. So of the 3 basic parameters that describe a galaxy, you have found two diameter and luminosity. The third, as was the case for stars, is more difficult to measure. So here we can see a good example. I might ask this in tests and exam as well, but basically the Hubble law. So the apparent velocity of recession of a galaxy, so VR, in kilometers per second is equal to the Hubble constant, h, multiplied times the distance to the galaxy d in megaparsecs. So here we have the velocity of recession equals the Hubble constant times d, the distance. So astronomers use this as a way to estimate the distance from a galaxy's apparent velocity of recession. So example, if a galaxy has a radial velocity of 700 kilometers per second, and we know the Hubble constant is 70 kilometers per second per megaparsecs, then the distance to the galaxy equals the velocity divided by the Hubble constant. So if we just solve the equation for d and plug in our values, we have 10 megaparsecs. Notice how the units in kilometers per second cancel out to leave the distance in megaparsecs. So there's one little trick I see here I want to teach you guys, especially going forward with your different modules you're taking. So if you are ever working, let me get something to draw with as we're working. So if you're ever working with equations, you need to solve it. So here we have our velocity of recession equals the Hubble constant times the distance. Never plug in these values from the beginning and then solve the equation. Never do it that way, because you can make an error, and then while you do your calculation, your error just becomes bigger, bigger, bigger. So the right way to actually do this is, if we have our equation, we first write down our equation, then we solve for the variable that we want. So you want d equals VR over h. And then the last step we do is, then we plug in our different variables. Because now we are the likelihood of us making a mistake and an error is much smaller. So it doesn't matter how long your equation is, you first solve it in variable form before you plug in your different values. The same thing with calculus. If you want to integrate something or differentiate something, try to keep it in variable form before you plug in everything. It will make your life a lot easier. I know that's a bit of a different mindset to get into, but it will make, in the long run, it will make your life a lot easier. Everybody still following? Awesome. So now, between high school and now, that's a weird different way of mindset to get into it. But trust me, in the long run, if you just plug in your different values at the end, at the final step, then you won't make any mistakes. So now the next property we're going to look at is mass. Before we take a look at it, do you guys want to take a quick 5-minute break? Or do you guys want to continue on? Okay, so 5-minute break. So let's continue this class at 6:40. So let's all return here back at 6:40. So while we are taking a break, how are your other modules going? That is good to know. So I know Physics 131 and WTW, that's a math module. I know that can be difficult. So something is, I sent an email to the HOD today asking if we can have a stargazing evening on campus one night. So fingers crossed it will be approved, but I will let you guys know what the HOD decides, all depending on the COVID protocols. But hopefully we'll have a stargazing evening on campus. So hopefully, so guys, keep your fingers crossed that the HOD gives us permission for stargazing evening. So where would we do that? Because I was looking for a high vantage point for the moon project just the other day. So that is actually a very good idea, because if we do a stargazing evening on campus, ideally we would need a power source so I can power up the motors on my telescope. It will make it just easier for observations. So I've also discussed this with the HOD, but one idea I have is probably the roof of the physics department, but I know the university has issues for people having roof access. But let's see what we can do. If you have any other ideas, then you're more than welcome to suggest them to me as well. Okay, so let's restart this class. Everybody back. Awesome. So now we're going to start talking about the mass of galaxies. So although the mass of a galaxy is difficult to determine, it is an important quantity. It tells you how much matter the galaxy contains, which in turn provides clues to the galaxy's origin and evolution. Although there are a few ways to estimate the mass of a galaxy, the most direct measurement uses Kepler's third law of planetary motion. In Chapter 8, Section 5, you use that law to find the masses of binary stars. If astronomers can measure the radius of a galaxy and the velocity with which it rotates, they can easily find the orbital periods of the stars in the orbit of the galaxy. So they can use Newton's version of Kepler's third law to calculate the mass of the galaxy. So the most accurate of these studies involve observing the rotation of the galaxy at different distances from its center and drawing a graph called the rotation curve of the galaxy. So here we can see an example of such a rotation curve. So in image A, we can see in the upper panel's artwork representation. An astronomer has placed the image of the galaxy over a narrow slit so that light from a galaxy can enter the spectrograph and produce a spectrum. A very short segment of the spectrum shows an emission line red shifted on the receding side of the rotation galaxy and blue shifted on the approaching side. Converting those Doppler shifts into velocities relative to the galaxy's center, the astronomer can plot the galaxy's rotation curve in the right. And then in image B, real data are shown in the lower panel. So galaxy NGC 2998 is shown over the spectrograph slit, and the segment of the spectrum includes 3 emission lines. The most accurate of these studies involve observing the rotation of the galaxy at different distances from its center and drawing a graph called the rotation curve of the galaxy. Using such a graph to find the mass of the galaxy is called rotation curve method. It is the most accurate way to find a mass, but it works only for nearer galaxies, whose rotation curves can be observed. More distant galaxies appear so small, astronomers cannot measure the radial velocity at different points across the galaxy. Measuring the mass of galaxies reveals 2 things. Firstly, the range of masses is wide, from 1 million times smaller than a Milky Way galaxy to 15 times larger. And second, galaxies contain dark matter spread through extended galactic coronae, just as does our Milky Way galaxy. One last region remains to be explored: what lies in the center of galaxies. Our Milky Way galaxy contains a 4 million solar mass black hole at its center. So do all galaxies contain similar objects? Rotation curve shows the motions of the outer parts of the galaxy, but it is also possible to detect the Doppler shifts of stars orbiting very close to the centers. Although these motions are not usually shown on rotation curves, they reveal something astonishing. Measurements show that the stars near the centers of most galaxies are orbiting very rapidly. To hold stars in such small short period orbits, the centers of galaxies must contain millions or even billions of solar masses in a very small region. The evidence shows that the nuclei of many galaxies contain supermassive black holes. The Milky Way contains a supermassive black hole at its center, and evidently that is typical of galaxies. So here we can see the first image taken again of from the Event Horizon Telescope of a supermassive black hole. So such a supermassive black hole cannot be the remains of a dead star. That would amount to only a few solar masses. Rather, a supermassive black hole either formed as the galaxy formed, or accumulated mass over billions of years as matter sank into the center of the galaxy. Measurements showed that the mass of a supermassive black hole is related to the mass of a central bulge. A galaxy with a large central bulge has a supermassive black hole whose mass is greater than a black hole in a galaxy with a small central bulge. Rare galaxies lacking central bulges usually also lack supermassive black holes. This suggests that a supermassive black holes formed long ago as the galaxies formed. Of course, matter has continued to drain into the black holes, but they do not appear to have grown dramatically since they formed. A billion solar mass black hole sounds like a lot of mass, but no, that is roughly 1% of the mass of the galaxy. The 4 million solar mass black hole at the center of the Milky Way galaxy contains only 1/1000th of 1% of the mass of our galaxy. Given the size and luminosity of a galaxy, astronomers can make a rough guess as to the amount of matter it should contain. But know how much light stars produce, and they know about how much matter there is between the stars, so it is quite possible to estimate the mass of a galaxy from its luminosity. But the measured mass of the galaxy is generally 10 times larger than is estimated from its visible. This must mean that nearly all galaxies contain dark matter. X-ray observations reveal more evidence of dark matter. X-ray images of galaxy clusters show that many of them are filled with very hot low-density gas. The amount of gas present is much too small to account for the dark matter. Rather, the gas is important because it is very hot and rapidly moving atoms have not leaked away. So evidently, the gas is held in a cluster by a strong gravitational field. To have a high enough escape velocity to hold hard gas, the cluster must contain much more matter than what astronomers can observe directly. The detectable galaxies in the Coma cluster, for instance, amount to only a small fraction of the total mass of the cluster. So here we can see in image A, the Coma cluster of galaxies contains 1,000 galaxies and is especially rich in E and S0 galaxies. So, giant galaxies lie near the center. Only the central area of clusters is shown in this image. If the clusters were visible in the unaided eye, it would span 8 times the diameter of the full moon. Then in image B, in a false colors, this X-ray image of the Coma cluster shows that it is filled with surrounded hot gas. So note that the two brightest galaxies are individually visible in the X-ray image, so I have no idea why it is called this way. So another way to detect dark matter goes back to 1916, when Albert Einstein described gravity as curvature of spacetime. The presence of mass actually distorts spacetime, and that is what you feel as gravity. He predicted that a light beam traveling through a gravitational field would be deflected by the curvature of spacetime, much as a golf ball is deflected as it rolls over a curved putting green, and that this would result in twice the deflection predicted by Newton's theory of gravitation. That effect has been observed and is strong confirmation that Einstein's theories is correct. So yes, you're probably right, they had a fun night when they discovered it. So couldn't neutrinos just be dark matter because they do have mass and there is lots of them? That is actually a good point. There are such theories, but nothing has been proven yet. So it's the most interesting name I've come across this far in astronomy. Yes, astronomy has some really weird and interesting names. Astronomers is not good at naming things. So gravitational lensing. So let me go on before we talk about this. Have you guys heard about gravitational lensing before? Okay, so let's talk about gravitational lensing. I think then you guys will have an understanding of what it is. So gravitational lensing occurs when light from a distant object passes a nearby massive object and is deflected by the gravitational field. The gravitational field of the nearby object is actually a region of curved space-time that acts as a lens and deflects the passing light. Astronomers can use gravitational lensing to detect dark matter when light from very distant galaxies passes through a cluster of relatively nearby galaxies on its way to Earth and is deflected by the strong curvature. The distortion can produce multiple images of the distant galaxies and distort them into arcs. The amount of distortion depends on the mass of the cluster of galaxies. So what is meant with that is, so here we have a quasar. So we all know a quasar is a very active galaxy. And so that means it is a black hole in the host galaxy, and the matter falling into a black hole is active. So here we have a distant galaxy, and here we have Earth, but we can see our, let me get something to draw with. So here we can see our view to that galaxy is blocked by the quasar. So what actually happens is light from this galaxy approaches the quasar, and due to its mass, it gets deflected. So that means it's being bent around the galaxy, and we can actually see it. And that means if you look this way, we can also see the galaxy, although light is being bent. And that is called gravitational lensing. Are you all happy with this explanation? Awesome. So observations of gravitational lensing made with very large telescopes reveal that clusters of galaxies contain far more matter than what can be seen. That is, they contain large amounts of dark matter. This confirmation of the existence of dark matter is independent of Newton's laws and gives astronomers great confidence that dark matter is real. Theorists conclude that dark matter must be made of some as yet undiscovered subatomic particles that do not interact with normal matter, with each other, or with light. Dark matter is detectable only through its gravitational field. So the question, sir, why does the light resume in the direction of its original course? It all depends on the gravitational field. So for example, in this image right here, the light is being bent this way. So if it continued straight, let me get something to draw with again. So that means the straight beam actually goes this way, and it actually goes this way. But now the light waves are being bent by gravitational lensing to form an arc that coincides with Earth, so we can see it. So what actually means is, if we have telescopes on Earth and we actually point it to here, we will see the galaxy. And if you point it to here, we will see the galaxy. Pleasure. So, as is seen in a video, this is just an artist's representation of dark matter, but this is actually not how it looks like, but it's just a cool image of artist's representation of dark matter. So dark matter is not an insignificant issue. Observations of galaxies and clusters of galaxies show that nearly 90% of the matter in the universe is dark matter. The universe you see, the kind of matter that you and the stars are made of, has been compared to the foam on the invisible ocean. Dark matter remains one of the fundamental unresolved problems in modern astronomy. So this is another hint for the tests and exams. I might ask you to name a couple of unresolved problems in modern astronomy, and this is one of them. So dark matter is an unresolved problem in modern astronomy. Just a hint for the tests and exams. So in image A, we can see the gravitational lens effect is visible in a galaxy cluster, as its mass bends the light of a much more distant galaxy to produce arcs that are actually distort images of the distant galaxy. This reveals that a galaxy cluster must contain large amounts of dark matter. And then in image B, when two galaxy clusters passes through each other, normal matter in pink collide with what's swept out of the clusters, but the dark matter in purple, detected by gravitational lensing, was not affected. So here we can put our different classifications of galaxies together. So we have our elongated galaxies, we have our spiral galaxies, we have our spiral barred galaxies. And here we have our irregular galaxies. So this is a nice family photo again of the classification of different galaxies. So now we're going to start talking about the evolution of galaxies. So considering the origin of our Milky Way galaxy, presumably other galaxies formed similarly. But why did some galaxies become spiral, some elliptical, and some irregular? An important clue that mystery lies in the clustering of galaxies. So here we can see again our best representation of the standard model and the Big Bang expansion. So bringing back to astronomy, cosmologists study galaxies and galaxy clusters and galaxy evolution. So single isolated galaxies are rare. Instead, most galaxies occur in clusters containing a few to a few thousand galaxies in volumes of 1 to 10 megaparsecs across. Our Milky Way galaxy is a member of a small cluster, and surveys has catalogued thousands of other clusters. For purposes of this study, you can sort clusters of galaxies into rich clusters and poor clusters. Rich clusters contain 1,000 or more galaxies, mostly elliptical, scattered through a volume of roughly 3 megaparsecs in diameter. Such a cluster is nearly always condensed. That is, the galaxies are more crowded near the cluster center. At the centers, such clusters often contain one or more giant elliptical galaxies. The Virgo cluster is an example of a rich cluster. It contains more than 1,500 galaxies and is 16.5 megaparsecs from our galaxy. The Virgo cluster, like most rich clusters, is certainly condensed and contains giant elliptical galaxy M87 at its center. So here we can see a image of the Virgo, so Virgo, laboratory for studying galaxy evolution. So here we can see this is not true color, but this just gives us the speed or radial velocity at which these galaxies are moving. So poor clusters contain fewer than 1,000 and often only a few galaxies spread through a region that can be as large as a rich cluster. That means that galaxies are more widely separated. So our Milky Way galaxy is a member of a poor cluster known by the imaginative name the local group. So here we can see our local group galaxies. So here we can see spiral galaxies, elliptical galaxies, irregular galaxies. So in image A, the local group, our galaxy is located at the center of this diagram. The vertical lines give the distances from the plane of the Milky Way are solid above the plane of the dash below. In an image B, the Sagittarius dwarf galaxy lies on the other side of our galaxy. So if you see it in the sky, it would be 17 times larger than the full moon. Then in image C, as shown in this artist's rendering of a mathematical model, the Canis Majoris dwarf galaxy has orbited around the Milky Way galaxy a number of times, and the tides has ripped stars and gas away as streamers. The total number of galaxies in a local group is uncertain, but it probably contains about 40 galaxies scattered irregularly through a volume of roughly 1 megaparsec in diameter. Of the brighter galaxies, 15 are elliptical, 4 are spiral, and 13 are irregular. The total number of galaxies in a local group is uncertain because some galaxies lay in the plane of the Milky Way galaxy and are difficult to detect. For example, a small galaxy known as the Sagittarius dwarf has been found on the far side of our own galaxy, where it is almost totally hidden behind the star clouds of Sagittarius. So even closer to the Milky Way galaxy is the Canis Majoris dwarf galaxy. This galaxy was found by mapping the distribution of red supergiants detected by the 2-mass infrared survey. There are certainly other small galaxies in the local group that have not been detected yet. In general, rich clusters tend to contain 18 to 90% E and SO galaxies and a few spirals. In other words, galaxies that are crowded together tend to be E or S0 rather than spirals. Poor galaxies contain a larger percentage of spirals. Among the rare isolated galaxies that are not in clusters, over 80% are spirals. Somehow the environment around a galaxy helps determine its type. Astronomers suspect that collisions between galaxies are an important process. So galaxies should collide fairly often. The average separation between galaxies is only about 20 times their diameter. Like two blindfolded elephants blundering about under a circus tent, galaxies should bump into each other once in a while. Stars, on the other hand, almost never collide. In the region of the galaxy near the Sun, the average separation between stars is about 10 to the power 7 times the diameters. Consequently, a collision between two stars inside a galaxy is less likely than a collision between two giant gnats fighting about in a football stadium. So, when we talk about colliding galaxies, there are 4 important points and a few new terms you guys need to take note of. So, firstly, interacting galaxies can distort each other with tides, producing tidal tails and shells of stars. They may even trigger the formation of spiral arms. So large galaxies can even absorb smaller galaxies, a process called galactic cannibalism. Secondly, interactions between galaxies can trigger star formation. Thirdly, evidence left inside galaxies in the forms of multiple nuclei and conflicting directions of star and gas motions reveals that they have suffered past interactions and mergers. And lastly, the beautiful ring galaxies are understood to be bullseyes left behind by high-speed collisions. Evidence of galaxy merger is all around you. Our Milky Way galaxy is a cannibal galaxy snacking on the nearby Magellanic Clouds. Furthermore, our galaxy's tides are pulling the Sagittarius dwarf galaxy apart, and the Canis Majoris dwarf galaxy has been almost completely digested as the tides have pulled stars away from great streamers wrapped around the Milky Way galaxy. So our galaxy has almost certainly dined on other small galaxies. So how are galaxies put together? So the test of any scientific understanding is whether you can put all the evidence and theory together to tell the story of the object studied. So can you describe the origin and evolution of galaxies? Just a few decades ago, it would have been impossible. But evidence from space telescopes and new generation telescopes on Earth, combined with advances in computer modeling and theory, allows astronomers to outline the story of the galaxies. Before you begin, you should eliminate a few old ideas immediately. It is so easy to imagine galaxies normally evolve from one type to another that you could call that as a common misconception. But an elliptical galaxy cannot become a spiral galaxy or an irregular galaxy because ellipticals contain almost no gas and dust from which to make new stars. So a question, so if a galaxy were to begin merging with other similarly sized galaxies, would it have any implications for us? That is actually a very good question. So depending on how close these stars move past each other, Earth's, for example, orbit can be destabilized, but there are a few actually simulations that is trying to investigate it. So if you just Google it, you'll find a few simulations. But a few of these theories said, yes, it will have implications for us, and other theories says, no, it won't have implication to us. It all depends on what is actually happening in the region around our own sun. So that means elliptical galaxies can't be young galaxies. But you can also argue that spiral and irregular galaxies cannot evolve into elliptical galaxies because spiral and irregular galaxies contain old stars as well as young stars. The old stars tell you that spiral and irregular galaxies can't be young. The galaxy classes tell you something important, but a single galaxy does not change from one class to another any more than a cat can change into a dog. Another old idea was that each galaxy formed from a single cloud of gas that contracted and formed stars, which astronomers refer to as a top-down hypothesis, as we talked about last night. So abundant evidence now indicates that large galaxies such as the Milky Way do not form primarily by top-down contraction, but instead by a bottom-up accumulation of smaller clouds of gas and stars, the inflow of gas and absorption of small galaxies. Ellipticals especially appear to be the product of galaxy collisions and mergers. They are devoid of gas and dust because it was used up in a rapid star formation triggered by the interaction or blown away by the erupt of supernovae. In fact, astronomers see many starburst galaxies that are very luminous in the infrared because a recent collision has triggered a burst of star formation that is heating the dust, which re-radiates the energy in the infrared. So some of these galaxies are 100 times more luminous than our Milky Way galaxy, but so deeply shrouded in dust that they are very dim at visible wavelengths. So here we can see in this image rapid star formations. So in image A is a starburst galaxy filled with clouds of young stars and supernovae. In image B, the dwarf irregular galaxy began a burst of star formation about 25 million years ago. Then in image C, at least some starbursts are triggered by interactions between galaxies. The innermost parts of M64, known as the Black Eye Galaxy, are filled with dust produced by rapid star formation. Radio observations show that the inner part of the galaxy rotates backward compared to the outer part of the galaxy, a product of merger, where the counter-rotating parts of the galaxy collide, star formation is stimulated. Many starburst galaxies show evidence of tidal tails and are probably the result of the merger of 3 or more galaxies that triggered firestorms of star formation and generated tremendous clouds of dust. The antennae galaxies contain over 15 billion solar masses of hydrogen gas and will become a starburst galaxy as the ongoing merger continues to trigger rapid star formation. As these galaxies use up the last of the gas and dust-making stars, they will probably become normal elliptical galaxies or merge to form a single elliptical. In contrast, spiral galaxies evidently have never suffered major collisions. Their thin disks are delicate and would be destroyed by the tidal forces generated during collision with a massive galaxy. Also, they retain plenty of gas and dust and continue making stars, so they have never experienced a major starburst triggered by a merger. Of course, spiral galaxies can safely cannibalize smaller galaxies with no ill effects. The small galaxies do not generate strong enough tides to disrupt the disk of a full-sized galaxy. You have seen plenty of evidence of cannibalism in our own galaxy, and some astronomers suspect that much of the halo consists of the remains of cannibalized galaxies. Evidently, our Milky Way galaxy has not collided with a galaxy of size comparable to itself so far. However, another evidence indicates that our galaxy will merge with the approaching Andromeda galaxy in a few billion years, and the final result will probably be a large elliptical galaxy. Paired spiral galaxies may also be the products of tidal interactions. Mathematical models show that bars are not stable and eventually dissipate. Tidal interactions with other galaxies they regenerate and sustain the bars. Well over half of all spiral galaxies have bars, suggesting that these tidal interactions are common. Other processes can alter galaxies. The S0 or SO galaxies may have lost their gas and dust as they orbit through the gas and the respective clusters. A galaxy moving rapidly through the thin gas filling a cluster would encounter tremendous wind that could blow the galaxy's gas and dust away. This is why a disk-shaped spiral galaxy could be reduced to an S0 galaxy. For example, X-ray observations show that a coma cluster contains thin, hot gas between the galaxies, and astronomers have located in the spiral cluster a galaxy in the act of plunging through such gas and being stripped of its gas and dust. Small galaxies may be produced in a number of ways. The dwarf ellipticals are too small to be produced by mergers, but they could be fragments of galaxies ripped free during interactions. Other small ellipticals may be the cause of large galaxies that had their outer stars stripped away during encounters. In contrast, the irregular galaxies may be small fragments splashed from larger galaxies during collisions, but retaining enough gas and dust to continue forming stars. A good theory helps you understand how nature works, and astronomers are beginning to understand the exciting and complex story of galaxies. It is already clear that galaxy evolution bears some resemblance to a pie-throwing contest. With the construction of the first large radio telescopes in the 1950s, astronomers discovered that some galaxies, dubbed radio galaxies, were bright at radio wavelengths. Later, when telescopes went to orbit, these galaxies were found to be emitting energy at other wavelengths as well. They became known as active galaxies. Modern observations show that the energy comes from the nuclei of the galaxy, which are now known as active galactic nuclei or AGNs. Only a few % of galaxies are active, but their activity makes them especially prominent. So this is what an active AGN will look like through a radio telescope. So if you look at the bottom, the image on the bottom, we will see our different stars and novae in the galaxy. But if we look in the radio part of the spectrum, we will see intense radio waves emanating from this galaxy. So here we can see as the center of the galaxy, and here we can see these two jets emanating from the center of this galaxy. It almost looked like it. That's true. So if we look at the center of one of these active radio galaxies, this is how it looks like the Lassila telescope, visible light, the infrared with Spitzer telescope, with the ALMA radio telescope, here with the VLA, Here with X-rays, radio, and visible light combined, and here is with X-rays in genre. So here we can see these galaxies are emanating a lot of power in different wavelengths. So do you think something like a Dyson sphere could come to be in our lifetime? Ooh, that is a really cool sci-fi question. So I don't think in our lifetime, but perhaps in a couple of thousand years. So before we continue with Seyfert galaxies, I think we can call this a night. So what is a Dyson sphere? So in sci-fi, is a concept where you can build a structure around your star. So for example, our own sun, we have the technology to build a structure around the sun. So Mr. Swanepoel, I like your definition or explanation, a star cage, so build a cage around the sun. And then you can use and harvest all the energy of that star, but that is just science fiction at this point, but that is called a Dyson sphere. So you can Google it if you want to. So I think we will call this for this evening. We will continue as lecture next week. So enjoy your public holiday tomorrow. I will remain active for another minute or two. Otherwise, have a great evening, and I will see you guys all next week. Remember, you guys will have a quiz next week. It will open up next week Monday and close the following Sunday. You will have a week to do it. I will also be on campus next week Tuesday for consultation again. So otherwise, have a wonderful evening, everyone. Enjoy your public holiday. Have a great week and good luck with everything. So I see no further questions, so I'm also going to log off. Have a great evening, everyone, and I will see you all next week. So question, so I had to reconnect at the start besides the quiz next week and the project. So yes, so there's going to be a quiz next week, and then the project is due end of May, and your semester test will also be at the end of May. It's a pleasure. So I'm also going to log off now. So have a great evening, everyone, and I will see you all. So I started my observations last week at around 1 a.m. The moon is only rising at 2 and 3 a.m. between today and tomorrow. Will it be a problem? So how many observations have you done so far? 7. Okay, so if you use software such as Stellarium, you can estimate where the moon will be and use that in your drawings. Pleasure. Okay, good night, everyone.